Hi everyone, in this recording we'll be going over the inverse of a square matrix. Our goal is that you'll be able to verify that two matrices are inverses of each other. You'll be able to use Gauss-Jordan elimination to find the inverse of a matrix. You'll be able to use a formula to find the inverse of a 2x2 matrix, and you'll be able to use the inverse matrices to solve systems of linear equations. A to the negative 1 is called a multiplicative inverse of A because A to the negative 1 times A is equal to 1. The multiplicative inverse of a matrix is defined in a similar way. So we let A be an n by n matrix, and we let In be the n by n identity matrix. So if there exists a matrix A to the negative 1, such that A times A to the negative 1 is equal to the identity, and that is also equal to A to the negative 1 times A, then A to the negative 1 is the inverse of A. And instead of saying A to the negative 1, we say A inverse. So for example, we are told to show that the matrix B is the inverse of the matrix A. So in order to do that, we need to multiply B times A and show that it is equal to the identity, and then switch the order, so now A times B, and show that that is also equal to the identity. So first we are multiplying A times B. So after following the steps that were defined in the previous recording, we get the identity matrix. Now, repeating the process for B times A, we also get the identity matrix. So that means that B is the inverse of A. So this is an example of a square matrix that has an inverse. Not all square matrices will have inverses. In this example, we are told to find the inverse of a matrix only given the matrix. So we are told that the matrix A is a 2x2 matrix with entries 1, 4, -1, and -3. So in order to find the inverse of A, we need to solve the matrix equation A times X is equal to I for X. And we know that a matrix multiplied by its inverse will result in the identity matrix. So setting that up, we have A right here. And then we have X, so we're going to do X11, X12, X21, and X22 because we're looking for an inverse matrix of A. And we're setting that equal to the identity matrix right here. So now, after completing matrix multiplication, we do this row by this column right here. And we're adding 1 times X11 plus 4 times X21. Now for the second entry in the first row, we do this row by this column, and we sum them right here. Now this one times this column right here, and then this row right here by this column. So now we set that equal to the identity matrix. So now we have two different systems of linear equations. So this portion right here is equal to this portion, and that's how we got this system right here. And this portion right here is equal to this portion, and that's how we got this system. So using the methods that we went over in previous recordings, we get that X11 is equal to -3 and X21 is equal to 1. So that is the first row of our inverse matrix. And now for the second row, we get X12 is equal to -4 and X22 is equal to 1. So that means that the inverse of A will be the following matrix: -3, -4, 1, 1. Now, to check that your answer is correct, we use a property that A times its inverse should yield the identity matrix, and the inverse of A times A should also yield the identity matrix. So first doing A times A inverse, we got the identity matrix, and now in the other order, first the inverse of A, then multiplying that by A, we also got the identity matrix, so our solution is correct. Now here's the other method for finding an inverse of a matrix. So we let A be a square matrix of dimension n by n. So now we can write the matrix with size n by 2n that consists of the matrix A on the left-hand side and the matrix I adjoint to A, so the identity matrix with size n by n on the right-hand side. So we get A on the left, and I on the right. So now, if possible, row reduce the augmented matrix until the left side becomes I. So the result will be the matrix, the identity on the left-hand side, and now the inverse will be on the right-hand side. So if this is not possible, then A is not invertible. So now we check our work by multiplying to see that A times its inverse is equal to the identity, and the inverse of A times A should also be equal to the identity. So here's the process that we just described with the example of A being a 3x3 matrix with the following entries: 1, -1, 0, 1, 0, -1, 6, -2, and -3. So first we had joined the identity matrix to A. So on the left hand side we had A, and on the right hand side we'll have a 3 by 3 identity matrix. So now using elementary row operations to obtain the identity on the left hand side and the inverse on the right hand side. This is the same method that we used when we were solving a system of linear equations when we were doing Gauss-Jordan elimination. And by doing that, we inherently got the solution on the right hand side. So the same concept applies, and we get the inverse on the right hand side right here. So the matrix A is invertible, and the inverse is that matrix right there. And we can check that solution by multiplying A times its inverse, and we see that we get the 3 by 3 identity matrix right here. To find the inverse of a 2 by 2 matrix, we can follow this simple formula, but it must follow this property. So if we're given the matrix A that is of size 2 by 2 with entries A, B, C, and D, then it is invertible if and only if A times D minus B times C is not equal to 0. Now the value A times D minus B times C is known as the determinant of A. So if the determinant of A is not equal to 0, then the inverse is given by the following formula. So A inverse is equal to 1 over the determinant of A times, so now the A and D entries in the matrix are switched from the original one, and now C and B stay in the same position, but now their sign is switched. So now they are negative if they were positive, and if they were positive, they are negative. Now we will use the formula that we just defined to find the inverses of the matrices, if possible. So for example A, we're given the matrix A with entries 3, -1, -2, and 2. So first we need to check that the determinant is not equal to 0. So A times D will be 3 times 2, so that's 6, minus B times C, so -2 times -1 is positive 2. So 6 minus 2 is equal to 4. So that is non-zero, so that means that we can find the inverse of the matrix. So then we'll use the formula 1 over 4 times the new matrix, so it'll be the A and D will be switched, so now instead of 3 we'll have 2 in the A spot, and now the -2 and -1 will now be positive, and instead of the 2 in the D spot, it'll be 3. So now we multiply 1 over 4 times each of those entries, and now we have the inverse. So now for example B, we're given the matrix B with entries 3, -1, -6, and 2. So we need to check that the determinant is not equal to 0. So we'll do 3 times 2 is equal to 6 right here, and minus -6 times -1 is equal to 6, so that is equal to 0. So it does not have the property that we need, so therefore we cannot find an inverse. So B is not invertible. Now we'll be able to go over the applications of matrix inverses and their role in systems of linear equations. So if A is an invertible matrix, then the system of linear equations represented by A times X is equal to B has a unique solution given by X is equal to the inverse of A times B. So here we're given an example. So use an inverse matrix to solve the system. X plus Y plus Z is equal to 10,000, 0.06X plus 0.075Y plus 0.095Z is equal to 730, and X minus 2Z is equal to 0. So first we began writing the system in the matrix form AX is equal to B. So A is the coefficient matrix, so we had all ones for the first equation, X plus Y plus Z. Then we had those decimal values for the second equation, 0.06, 0.075, and 0.095. And now for the third equation, we had a 1 for the X, a 0 for the Y, since there's no Y entry, and a -2 for the Z. Now we have our X, since we have 3 variables, X, Y, and Z, and we are setting that equal to the constants on the right, so 10,000, 730, and 0. So now we can use Gauss-Jordan elimination to find the inverse of A, and that is given by this matrix right here. Now using the formula that we just defined, X is equal to the inverse of A times B. So we saw that the inverse of A was this 3 by 3 matrix, and we defined the column matrix B by the constants right here, the 10,000, the 730, and the 0. Now multiplying those two matrices, we get the X matrix. So that one has the entries 4,000, 4,000, and 2,000. So that means that the solution of the system is x is equal to 4,000, y is equal to 4,000, and z is equal to 2,000.